Hello, I'm Brahmani from ECA. Today we're going to discuss about the introduction of the features section on photonic crystal structures and applications. So this is all about the feature section on photonic crystal structures and their applications. So here we can see briefly about this in the next slide. Introduction to photonic crystal structures. Photonic crystal structures are optical materials with a paired structure and that affects the photons. They control light on a scale comparable on the wavelength of light, enabling unique optical properties. Applications of photonic crystal span from telecommunications to biosensing technologies. Also, so basically, photonic crystals are optical materials with a periodic structure that affects the motion of photons. They can control light on a scale comparable to the wavelength of light, enabling unique optical properties. Applications on photonic crystals span from telecommunications to biosensing technologies. We can also observe the pictures of photonic crystal structures here. Basic principles of photonic structure. The periodic arrangement of materials creates a photonic band gap that prohibits certain wavelengths from propagating. This band gap can be engineered by varying the geometry and refractive index of the materials used. Understanding these principles is essential for designing devices that utilize photonic crystals effectively. The periodic arrangement of materials creates photonic band gap that prohibits certain wavelengths from propagating. Understanding these principles is essential for designing devices that utilize photonic crystals effectively. Types of photonic crystals. Photonic crystals can be classified into two-dimensional and three-dimensional structures based on their dimensity. Two-dimensional photonic crystals are often easier to fabricate and widely used in integrated top optics. Three-dimensional photonic crystals exhibit more complex behaviors and are suitable for advanced applications such as laser systems. These are the types of photonic crystals, and here we can see there are classified into two-dimensional and three-dimensional based on their dimensionality. Two-dimensional photonic crystals are easier to fabricate and widely used in integrated topics, whereas three-dimensional structures are more complex behaviors and suitable for advanced such as laser light and etc. These are advanced and complex applications, and these are easier to fabricate and widely used in integrated optics. Fabrication techniques. Common fabrication methods include lithography, self-assembly, and direct laser writing. Common fabrication methods means lithography, self-assembly, and direct laser writing. Each technique offers different advantages in terms of scalability, precision, and material compatibility. The choice of fabrication method significantly impacts the performance and applicability of the resulting photonic. Here, in fabrication technique, we can observe that common fabrication methods and there are different advantages such as scalability, precision, and material compatibility. There are different techniques for each thing, and the choice of fabrication method significantly impacts the performance and applicability of the resulting photonic crystal. The choice of fabrication. Sorry. Optical properties. Photonic crystals exhibit unique optical properties such as refraction, negative refraction, and slow light effects. These properties arise from the interaction of the light with the periodic structure of the crystal. Understanding these optical phenomena is crucial for developing devices with enhanced performance crystal characteristics. Means here we can see the optical properties of the photonic crystals. They exhibit unique optical properties such as negative refraction and slow light effects. Slow light effects, negative refractions. These are the some unique optical properties of photonic crystals, and these properties arise from the interaction of light with the periodic structure of the crystal. They arise from the interaction of light with the periodic structure of crystal. With respect to the periodic structure of crystal, the above said properties such as negative refraction, they will arise. Understanding these optical phenomena is crucial for developing devices with enhanced performance characteristics. For developing devices, these optical phenomena, will be there. No, there are some crucial to understand and to perform their characteristics. These are some pictures of this. Is a refractive index, and this is the coating and cladding, and this is the core. We can see here again refractive index. This one is the outliers, which is called refractive index, and this one is coating, and this is the core optical properties. And next, applications in telecommunications. So basically, optical fiber is widely used in telecommunications. It is the easiest way and it helps a lot to telecommunicate things. And in that, we use photonic crystals. Photonic crystals are integral to the development of advanced optical fibers and waveguides. They enable efficient light manipulation, which is essential for high speed data transmission. The use of photonic crystals in telecommunications can lead to significant improvements in bandwidth and signal quality. Photonic crystals are integral to develop the advanced optical fibers and waveguides. So, as I said, they are the things which are used to develop the advanced things in optical fibers and waveguides. They enable efficient light manipulation, which is essential for high speed data transmission. Efficient light manipulations means more efficient light manipulation. They help things like essential for high speed data transmission. The use of photonic crystals in telecommunications can lead to significant improvements in bandwidth and signal quality. These are the applications in telecommunications and biosensing applications. Photonic crystals can be employed in biosensors to detect the biological molecules with high sensitivity. Their unique optical properties allow for real time monitoring of biochemical reactions. This capability has significant implications for medical diagnosis and environmental monitoring. So, basically, photonic crystals can be employed in biosensors to detect biological molecules with high sensitivity. They are already employed in biosensors. They are used to detect the biological molecules with high sensitivity. Means they can capture every single minor sensitive detail. Like they are much sensitivity. They are having much sensitivity. Their unique optical properties allow for real-time monitoring of biochemical reactions. The crystals will have some optical properties, right? They will allow the real-time monitoring of biochemical reactions. This capability has significant implications for medical diagnosis and environmental monitoring. This also helps for medical diagnosis and environmental monitoring, like whether something environmental monitoring and medical diagnosis. They are useful. And photonic crystal lasers. Photonic crystal lasers utilize the photonic band gap to enhance light emission and reduce the threshold current. These lasers are known for their compact size and high efficiency compared to traditional laser designs. Their applications range from consumer electronics to industrial laser systems. Challenges and limitations. The fabrication of photonical crystal structures can be complex and costly, limiting their widespread adoption. Additionally, achieving the desired optical properties in a practical device remains a significant challenge. Ongoing research aims to address these limitations and prove the scalability of photonic crystal technologies. Basically, in this slide, we can see lasers of photonic crystals. The photonic crystal lasers utilize the photonic band gap to enhance light emission and reduce threshold currents. They'll use band gap to enhance to allow more light emission and to reduce threshold currents. These layers are known for their compact size and high efficiency compared to traditional laser designs. Size and high efficiency compared to traditional layer designs, as we said, we can know that. Their applications range from consumer electronics to industrial laser systems. Their applications range means they're applicable for consumer electronics to industrial laser systems. Means very small to very big. They are applicable. And these are the challenges and limitations. Future directions. Future directions of photonic crystals lies in their integration with nanotechnology and quantum computing. Emerging applications include optical signal processing and advanced imaging systems. Continued innovation in materials and fabrication techniques will unlock new possibilities for photonic crystal structures. The future of photonic crystals lies in the integration of nanotechnology and quantum computing. It's always based on nanotechnology and quantum computing. The versions and the new technologies can develop them. Emerging applications include optical signal processing and advanced imaging systems. Emerging applications they include optical signal processing and advanced imaging systems. Continued innovation in materials and fabrication technologies will unlock new possibilities for photonic crystal structures. These are the future directions of photonic crystal structures. And that's it. We can see here everything. Crystals. Photonic crystal structures control light on scale comparable to wavelength of light, enabling optical properties. This is the recap, and that's it. Thank you.